Welcome to Online Algebra 2. This is section 5-1, Polynomial Functions. So our objective here is to classify polynomials and to graph polynomial functions and start to describe properties of the graph, especially their end behavior and turning points. So what you need to know is that a polynomial function has distinguishing behaviors, things that the graph does that we can determine based on the equation. So you can look at the algebraic form and know something about its graph. You can look at its graph and know something about its algebraic form. Okay? So first we need some vocabulary. And polynomials have a lot of vocabulary. So first thing we're going to talk about is something called a monomial. Right? Mono meaning one. So it is a real number, a variable, or a product of a real number and one or more variables with whole number exponents. So this is a monomial because it's a real number and a product of a real number and a variable. That is a monomial. This is a monomial because we're still a product, 2 over 3 times x squared. As soon as we do this, now that's not a monomial anymore, right? Then this is more than one term, okay? Remember that terms are separated by addition or subtraction, but addition with a negative number. So in order to have more than one term, we need to have an addition sign somewhere in the problem somewhere. If it's just all multiplication and division, then it is a monomial. And this is not a monomial because that is not a whole number exponent. Okay? So the degree of a monomial in one variable is the exponent of the variable. So back to the first example, or something close. The degree of this monomial is 3. Okay? The exponent of the variable. Okay? If we have more than one term, then we can call this a polynomial, and we have special names for different types of polynomials that we do in the next page. So a polynomial is a monomial or a sum of monomials, and the degree of a polynomial is still 3. It's still the biggest exponent, the greatest degree among its monomial terms. And a polynomial with a variable of x defines a polynomial function of x. If it's a polynomial with a variable y, it's a polynomial function of y. And the degree of the function is the same as the degree of the polynomial. Okay, so when we have the standard form of a polynomial function, it looks like this. And you're going to see that equation a lot in this chapter. Okay, it's not something to get intimidated by. All right, so the basic thing you have to realize here is it arranges the terms by degree in descending numerical order. So what that means is that is the biggest degree. This one is one less, might not be one less, but it could be, right? This could be a 0 coefficient in the front, and then that term would just go away, right? And then one less, and then one less, and then one less, and one less. That's what these ellipses are saying. Everything in between to the first power, and then to the 0 power. So we're covering every possible term, every possible exponent term. Excuse me, every possible exponent term of x. Now, these terms are my coefficients. Okay? The subscripts there are just saying this coefficient is the one that is with this degree term. You don't write them, you just write a number, right? But what it's saying is that these things don't have to be all the same. They could be anything, it doesn't matter. They could be the same, but they don't have to be the same. when we write it out with numbers, it looks a little nicer, right? We have 4x to the third, 3x squared, 5x minus 2. These are all different terms because they're all separated by addition, right? Plus a negative 2. These are all the different coefficients. This is the coefficient that goes with the third degree term. 3 is the coefficient that goes with the second degree term. 5 is the coefficient that goes with the first degree term. And 2 is the constant term, or the one that goes with the 0 degree term. And notice that these all have special names. In fact, polynomials get 2 names. And we name them first by degree. So if the degree number is 0, that is called a constant. If the degree is 1, it's called a linear, like we studied in chapter 2 and chapter 3. If it is a degree 2, if it's something squared, then that is a quadratic, like we studied in chapter 4. Okay? Then my names go, for 3, it is cubic. For 4, it is quartic. 5 is quintic. And then anything above that, we just say 6th degree, 7th degree, 8th degree, nth degree, whatever. Doesn't matter, okay? So we use special words for the first 6 here. Now there's other names for 6 is sextic, 7 is septic, octic, nonic. But typically, these are the most common. These two we'll also use, not quite as common as the first couple, but definitely something that we're going to use. Anything above 5, though, we're just going to use a number degree, 6th degree, 7th degree. Okay? So the first name of a polynomial is one of these words, or a number with a degree. The second name is how many terms are there? Like we just said before, if there's one term, it's a monomial. If there's 2 terms, and you probably heard, most of these should be familiar, binomial. 3 terms is a trinomial. And then anything 4 or more, right? So polynomial 4 or more is going to be a polynomial of 4 terms, 5 terms, 6 terms, 7 terms, however many of terms there are. But you should definitely say a polynomial. You just shouldn't say a polynomial. You should say polynomial of so many terms. Okay? So, write each polynomial in standard form. Okay, that's what we're going to do first. So before we name a polynomial, okay, we need to rearrange it, and we also need to combine any like terms. Okay, so first thing to do, standard form, is biggest exponent goes first, then the 3x, then the 5. So that is the polynomial in standard form. What is the classification of each polynomial by degree, by number of terms? Those are its 2 names. So this is x squared. So that is a quadratic. And it's 1, 2, 3 terms. Quadratic trinomial. Okay. For part B, I would be tempted to say it's 5 terms, but it's not. We have x to the 4th. There is no x to the 3rd, but the x squareds can go together. So that's going to be plus 4x squared plus a 4x and a minus 12. So instead of being a 5-term polynomial, it is down to 4. So it is degree 4. So this is a quartic polynomial of 4 terms. Oops, I'm going to space a little bit there. These two, again, oops. That one's first. So that's 5x to the fourth plus 3x to the third minus x, no like terms. That is a quartic trinomial. Okay. And for the last one, we have our leading term as negative 4x to the fifth plus 2x squared plus 13. So this is a quintic, fifth degree trinomial. Okay. And we can name any polynomial up to however many of terms that we possibly have. Okay. Besides the name, the degree of a polynomial function also affects the shape of its graph and determines something called turning points, or places where the graph changes direction. It also affects the end behavior, or the directions on the far left or the far right of the graph. So when we look at these different examples here on this table, it shows us examples of polynomial function and the 4 types of end behavior, right? A polynomial graph, if we think about it, is this lead term right here. Again, let's just keep it simple. Right? If I'm plugging in numbers for x, 3x plus 1, 3 times the number plus 1, these two terms are not really going to make my answer that much bigger. This will, right? Because, you know, even just plugging in like a 2 or a 3 or a 4, when we raise it to the 5th power, it's going to make that number much, much bigger, or in the terms of a 5th power, much, much smaller than the rest of, than these two terms right here. This is always just going to be a 1. This is going to be 3 times something, right? The 5th power is always going to be much bigger or much smaller. So this thing right here is going to have the most effect on the graph. And what the graph is going to look like is it's going to look like the graph starts to go straight up, or not straight up, but it's going to be going up very sharply or down very sharply. Okay. And that's what we call end behavior, either up or down to the left and to the right. This table also shows us intervals where the function is increasing and decreasing. That is pretty obvious based on the graph. If we read a graph left to right, which we always do, you should be able to tell if the graph is going down or up. And we're really not going to worry too much about finding the exact points of inflection, but know that there is a way to tell how many times a graph could change direction from increasing to decreasing. Function is increasing when the y values increase as x increase, and decreasing when the y values decreases as x increases. That's what. So what we can do with this is look at this first term here. It is a 4x to the 4th power. Notice that both ends of this function are going up. Okay, and you know we can see that it does happen to have 3 spots where it changes direction. Okay? We don't need to know exactly what they are, but we just need to know that it happens. This lead term is a negative x squared. Notice that both ends go down, and it only turns once. Okay, so that maybe sets up a little pattern for us where this lead exponent could tell us something about where the graph is going to go. And I have a whole chart about that in a second. Okay, let's look at these two. Now, both of these exponents are 3rd powers. Notice that this side goes down, this side goes up, and the opposite is true here. If you notice carefully, what's the difference in this lead term? Well, one of them is positive and one of them is negative. Back up to the top here. That one is positive, that one is negative. Okay, so there is a relationship between the sign of the leaded coefficient and the type of exponent that you have, an even number or an odd number, when it comes to the end behavior of my function. And here is the chart for that. So we can determine the end behavior of a polynomial function of degree n, whatever my degree is, from the lead term. So just the thing in the front of the polynomial. And we look at two things. We look at A, the coefficient. Is it positive or negative? And we look at n, the exponent. Is it even or odd? And then this is left, this is right. So if it's positive and even, the left side goes up, the right side goes up. Negative and even, both sides go down. If it is positive and odd, the left side goes down, the right side goes up, and vice versa for this too. The way I like to remember this is even exponents go the same direction. Think of the parabolas. Okay, so there's a parabola. If the lead coefficient of a parabola is positive, I know that opens up, and now both ends go up. All right, and so again, if it's a negative in the front, I know that parabola opens down, and it's true for any even exponent. For odd exponents, I know they're going to have to go in a different direction because I should kind of know this function already. The cubic parent function, and we'll get into that a little bit more, but hopefully you've seen that a little bit before. So I know both sides have to go in different direction. And the way I like to remember it is if it's positive, it's going to end positive. If the lead term is negative, it's going to finish negative as I go to the right, as I get bigger numbers into this function. Okay? So in general, the graphs of polynomial function of degree n, right, as long as n is greater than or equal to 1, right, we're not talking about negative exponents here or zero exponents, has at most n minus 1 turning points. So if we look back here again, this is a fourth degree. It has at most one less turning point. This is a second degree. It had one turning point. Well, this one didn't turn at all. It keeps going up. That's okay, but it could have had two, like this one. Okay, so this theorem doesn't tell you how many turning points a polynomial has. It tells you how many it could have. And the graph of a polynomial function of an odd degree has an even number of turning points. Okay, because both ends have to go in different directions. So it either turns it doesn't turn at all, or it turns twice. It can't turn once, right? If a graph only turns one time, both ends go in the same direction. I need a polynomial to turn once, twice, in order to be a odd degree, right? An odd degree has an even number of turning points. An even degree has an odd number of turning points for the same reason. Okay? And again, this is not telling me what those turning points are. It's not telling me much. But what it is doing is it's letting me get an idea of what the graph could actually look like when we graph them. Okay? So let's do this. Consider the lead term of each polynomial function. What is the end behavior? And you could check it with a graphing calculator if you wanted to. Make sure it's in standard form. Make sure you've written the polynomial the right way. The 4x to the third is my lead term. So that means, going back to the other stuff we just learned, this is a cubic binomial. And we always go like this, left side first, and then the right side. So it's odd, it's positive, the left side goes down, and the right goes up. There's fancier ways to write that, like with using limit and arrow notation, but we'll save that for another time. Again, the first thing you have to do is make sure this is in standard form. It is. That's my focus, the lead coefficient. If I wanted to name it, this would be a quartic polynomial of 4 terms. For now, this is a negative, this is even, so the left side goes down, and the right side goes down. Okay? So no matter, this graph could turn 3 times. Doesn't have to, but it could, as long as the left side goes down and the right side goes down. We could have some sort of graph that looks like that. Not saying that's what it looks like, probably is not even close, but I do know for sure that these two go this way. I got a problem? Again, focus on the lead term. It is a negative. It is odd. That means that the left side goes up and the right side goes down. All right, so let's graph some functions. Okay. Now, just by looking at this cubic function, I'm going to say that I already know a little bit, well, I do know what it looks like, but you should know a little bit about what this looks like already. It's a 3rd degree polynomial. The number in front is positive. That means the left side goes down, the right side goes up. It could turn twice or less. So 2 or 0, pretty much. Okay, so because I don't know anything else about this thing, I'm going to use the most basic method that I have to graph this function, and I'm going to make a table. Okay, I'm going to plug in -2, raise it to the 3rd power. -2 to the 3rd power is still -8, so that's -4. I'm going to plug in -1, raise that to the 3rd power, and we get -1/2, right? 1 to the 3rd power is -1. Plug in 0, I get 0. 1 gives me 1/2, and 2 gives me 4. I could plug in 3, but 3 to the 3rd power is 27, and that's not quite on this graph. Okay, so let's plug in my numbers. -2, -4, -1/2, 0, 1/2, 4, and I have a graph that looks like that. Hey, look at that. The left side goes down, the right side goes up, just like I thought. It never changed directions. So, and this graph is constantly increasing. Okay. So, I had a little bit of a picture beforehand, and now I have a pretty decent picture of what this graph looks like now that I've graphed it. Let's try this one. First of all, we need to change it around because that's my lead term. That's what I focus on. So I know that it is negative and odd. So that means this side goes up, this side goes down. Doesn't tell me anything else about the graph, but it does let me at least make sure I'm not messing anything up. For now, my technique is plug numbers in. -2, right? -2 to the 3rd power is -8. That negative out front makes it a +8. And that's -6, so that's going to be 2. So I'm just plugging the numbers in. Plug in -1, we get -2. Just remember that we're cubing the -1, and then making the negative again, right? It's not, right? It's not that. So we don't include this negative in the cube until after when we multiply. Plugging in 0 is easy, gives me 0, 0. Plug in 1, I get a +2. And if I plug in 2, I get a -2. So that should be enough data to graph this thing. I expect the left side to go up, the right side to go down, and this could turn twice. So let's see. -2, 2. -1, -2, 0. 1, 2. And 2, -2. Oh, that looks weird. But remember, we're going to go left to right. And right? If we just follow the dots, I get my graph that looks kind of like that. Now, a couple things here. These are polynomials, so they don't have any sharp angles, okay? So when you're drawing polynomials, realize that it's going to curve, okay? So, and if you do draw it by hand, try to make them curve. Polynomials have no breaks in them, and they have no sharp turns, okay? Or else it's not a polynomial. The other thing is that these points, these turning points, are the best estimations that I got from graphing this by hand by plugging in numbers that are easy to work with. If you want to plug in or use a graphing calculator, you could find exactly where these turning points are, but sometimes our graphs are not going to be perfect, right? They're just going to be estimations. Finding the turning points, we could do that, but it takes calculus, okay? So we're not there yet. Okay. So one other thing we can do with these polynomial functions is figure out the degree if we're given raw data. So suppose you're given a set of polynomial function outputs. You know that their inputs are an ordered set of x values, so they're in order, in which consecutive x values differ by a constant. So the x values are 1, 2, 3, 4, 5, 6, 7. There's some sort of pattern in the x values. By analyzing the differences of the consecutive y values, you can determine the least degree polynomial function that could generate the data. So if the first time you do differences, which means subtraction, so if the first time you subtract, all the differences are the same, it's a linear function. If it takes 2 times, it's quadratic. If it takes 3 times, it's cubic. Okay? Let me show you what I mean. So notice the x values are in order. -3, -2, -1, 1, 2, 3. Okay, they all differ by 1. That's good. Okay, so now what we want to do is we want to take these two and subtract them. So -7 minus -1, which is, it is -6. Remember, we're subtracting the y2 minus y1. So -3 minus -7 is 4. 5 minus a -3 is 8. 11 minus 5 is 6. 9 minus 11 is -2. And -7 minus 9 is a -16. Everybody else has trouble with the subtraction whenever I do this. But remember, we're subtracting the second one from the first one. And don't forget, minus and minus is plus. This is the first difference. Notice they are not all the same. So that means you do it again. Okay, 4 minus -6 is 10. 8 minus 4 is 4. 6 minus 8 is -2. -2 minus 6 is -8. And -16 minus a -2 is -14. 14. These are not the same. That was difference 2. So that means you try again. 4 minus 10 is -6. -2 minus 4 is -6. And look at that. So the third difference was the one where I have all constant terms. That means this data is a cubic function. Okay. So again, you have to just go through and keep trying to figure out which set of data or which set of differences is constant, and then this will tell you what kind of polynomial made this data. Okay. And that is, nothing much here I wanted to cover. That is 5-1, polynomial functions.